So I just do things component-wise, and then, of course, everything works out. I get the laws, the category will work out for free. And that notion of the product agrees, of course, with the product of groups, the product of pose sets, and so on. And we're going to see next time that that's not just an accident, that's actually determined by the laws of products in general. Another example of a construction on categories is the arrow category. So given a category C, the arrow category of C has as objects are the arrows of C. So let me say A, F, A prime, arrows of C. Arrows. And the arrows, those are the, oh, I forgot to do something. Let me go back in a minute. The arrows are going to be F, A prime. Here's another one, B, G, B prime. So those are two objects, and an arrow between these two objects is going to be a pair of arrows like this, making a commutative square. That is, a pair of let me say this arrow, I'll call it alpha. It has a first component and a second component, alpha 1 and alpha 2, or let me say, notation's not good, sorry. Yeah, okay, alpha 2, such that by commutative square, I just mean going around both ways gives the same thing, right? Alpha 2 after F equals G after alpha 1. So an arrow in this category is a commutative square in C. An object in the arrow category is an arrow in C. An arrow in the arrow category is a commutative square in C. Okay? It's just kind of a compound operation there. And obviously, you can keep going in that way. Do I have another board here? No, I used that. I forgot a very important thing. How could I forget that? I should have squeezed in here something else. So, the motto of category theory, I guess, something like that. The motto or the slogan. The slogan of category theory is, somebody want to guess what the slogan of category theory is? It's something like, it's the arrows that count, right? Not just the objects, but the arrows. The relations among the objects are given by mapping one to another. That's what the arrows do. They map one object to another. And that's what really determines the structure of the objects, is the way you can map them or relate them to each other. So the arrows count. So, of course, the first thing you should ask if somebody gives you some new kind of mathematical structure or logical construction is, what are the maps between them? What are the arrows between them? Because that tells you what parts of the specification are relevant, right? Sometimes you specify some new kind of structure or data type or something in a way that requires a bunch of auxiliary machinery, but you don't really care about all that. You only care about certain aspects of it. But to care about an aspect is something in your head, right? It's not a mathematical thing. To make it into a mathematical property, you specify what the arrows are, and the arrows will then determine what aspects get preserved, what aspects count, and what aspects can be thrown away or don't count. So given that, as soon as I've defined over there what a category is, you should ask me, what are the maps of categories? Right? And that's a functor. So a functor, that's the idea of a map of categories. Functor F from one category C to another category D, what is that? Well, just like a category has two parts, objects and arrows, a functor also has two parts. So officially, although I'll never write this again, it has a part that takes the objects of C to the objects of D, so it's a mapping. And then there's this other part, the arrow part. Let me say, this is the object part, this is the arrow part, which takes the arrows of C to the arrows of D, plus some laws which are best illustrated diagrammatically. That is, if I have here A, F, B, GC, and then here's the composite G after F, and here, say, is the identity on A, and I apply the functor F, so this whole diagram is living in the category C. I apply the functor F, I get something over here in the category D. It looks like this. Well, the functor applies to objects to give new objects. It applies to arrows to give new arrows. And a condition is it preserves domains and codomains. So the domain of this arrow is this, the codomain is that. Therefore, because the functor is required to preserve domains and codomains, this will all line up. And then the further condition is, well, as you might guess, it preserves identity maps. So the identity, the F applied to 1 of A is required to be equal to 1 of F of A. And finally, it preserves composition. So F of G after F is required to be equal to F of G after F of F. So it just preserves all the data in the definition of a category. That's what a functor is. Preserves the objects, the arrows, the domains, the codomains, the composition, and the identity maps. Okay, so that's the basic notion of a functor. And now let's observe that, for example, here, there's a functor from the product category down to C. It's just a projection in the first component. Right? And just the way I've set this thing up, you can see that it's a functor. Right? It's obviously, it preserves domains and codomains, it preserves identities, and it preserves composition, just because of the way that product category is defined. Similarly here, if you look at the arrow category, you can work out for yourself that there are two functors here. One that takes the domain of an arrow. So here's an arrow, and there's a functor that just takes the domain of the arrow. And there's another one that takes the codomain of the arrow. And now the trick is to show or to observe that those things really are functors. So those are some examples there of functors on those derived constructions. We have another kind of example. Yep. What would it mean to leave them off?
C arrow is including this alpha 1, alpha 2 in the map.
So an arrow, the definition of an arrow from do it right here. So here's F, right? Let me write it like this. And then I'm saying, what is an arrow from F to G in the arrow category? C arrow. What is this? And what I'm saying is, just to transpose the picture to make it, just to get your head working in a different way, because sometimes it's good to think about things in different ways. So here now I've written this object over here, and here's this other object over here. A prime, okay. B prime. Here's this other object over here. And now I have to say, what is an arrow from here to here supposed to be, right? And what I've said is, well, it's by definition a pair of arrows, one here and one here. Give them some names, alpha 1 and alpha 2, such that this square commutes. So I don't know what it would mean to leave the alpha 1 and alpha 2 off. Okay?
Yeah.
Another kind of category, it's called a slice category. So take A to be any object in some category C. Then we make a slice category. This is going to be, this comes up all the time, strangely enough, but it's going to be used in the very last lecture when we do the categorical semantics for dependent type theory. A slice category, which I write like this, C sliced over A, has as objects, it's kind of like the arrow category, arrows, but they're always arrows with A down here in the codomain. And then as arrows, here's another one. As arrows, it has commutative triangles. Arrows. The objects are the F's, and the arrows are the alphas. Okay, so instead of the rectangle, we just require, you can think of it as requiring this to always be the identity map down here. And then this is a special case of that. Okay, and then it's a category for the same reason as the other one is a category. And there are some interesting functors here. There's a functor, kind of a so-called forgetful functor. It goes from the slice category down to C itself. It just says forget this indexing here over A. It's basically the domain functor, right? And another thing that you can do is this. Look, let's suppose we have a map here. Let's make this our, let's make this FG alpha, what am I going to call this? K here, from A to A prime. Given any map like this, I get a functor C A to C over A prime. I'll call this K shriek. How does it work? So this is just an object in C. This is an arrow in C. This is a whole category, right? And now this is a functor from this category to this category. It works like this. Here's A. Here's F, G with its domain and codomain. And it works by composition. Here's K. So if this is a commutative triangle, now I take this commutative triangle over here to 1 over A prime. I just compose with K. So this is my definition of K shriek of F. It's K after F. Similarly here, K shriek of G. And now, if this triangle commutes, well, this one commutes by definition. This one commutes by definition. And so this is a little diagram chase, right? A diagram chase says you have to show that two arrows are equal, namely this one and this composite, because that's the definition of an arrow, right? An arrow from this composite to this composite is a thing across the top on the domains, making the outer triangle commute. But we know that this one commutes, and this one commutes, and this one commutes. And so to show that this composite is equal to this arrow, we can go like this. We say, this composite that we're interested in is really the same as this followed by this followed by this, by the commutativity of that triangle. That's the same as this followed by this by the commutativity of that triangle, and that's the same as this arrow, which is what we wanted to show by the commutativity of that triangle. So that kind of arguing on diagrams is a very useful technique when you have to do kind of equational reasoning in a complicated situation. Of course, you could just do it with equations, but the diagram helps you keep track of what order to do the equational reasoning in. It's just a simple example, but you can imagine much more complicated examples.
Yes.
Is there some symbol that you're using there for the functor that you built out of K? I can't see it.
Shriek. Bang.
Bang? Okay, all right.
And I'm told that Whitehead called it shriek.
And what's the name for this whole widget?
The whole widget is the slice category, and I'm just observing that the slice category is functorial in this argument. And now you can go even further. I said for each object in the category, you get a category. So we're fixing C. Now for each object, we get a category, C over A. For each arrow, K B, we get a functor, C, B. Okay, sure. So we have an assignment, takes objects to categories, arrows to functors. This is living in C. What is this? That's a category, and that's a functor. That's a diagram in cat. Cat is the category of categories. It has as objects categories and as arrows functors. I didn't mention that one before, did I? But it's obviously a category, isn't it? The objects are categories, the arrows are functors. The composition is just composition of functors. Okay? It's like functional composition because these things are functions in each argument. And because of the way I've defined it, just like for posets, it's associative and it satisfies the unit law. So that's a category, full stop. And now this assignment is a functor. It takes an object of C to a category, it takes an arrow to a functor, and the whole thing gives a functor from the category to the category of categories and functors. That's a homework exercise for you. Just to kind of keep all the balls in the air, right? Just to get used to these concepts. Anyone have some foundational queasiness at this point? Yeah.
One more time.
What's that?
Could you go over that last thing one more time?
What this is?
Yeah.
This is the category C. Here's an object of C. Here's another one. Here's an arrow of C. Okay? I've given you an assignment for each object of a category. Namely, the slice category consists of these triangles. And then for each arrow, there's a functor which goes from here to here. It's this functor. Okay? It's this operation. It takes triangles over A to triangles over A prime. And now I'm saying that assignment, which takes objects and arrows as categories and functors, is itself a functor from the category C into the category of all categories. The objects of categories and arrows. So you have kind of three different levels going on here. Yep.
So I don't quite have the intuition for the slice category and the forgetful functor.
It'll come. Just do the homework exercise.
Okay.
We'll have some intuition later on when we talk about dependent type theory. The intuition for the slice category, really, or at least one intuition for it, is that you think of these things as families varying over this index. One intuition. Think of this, if this is a continuous function, for example. Now there are some points here, and for each point, you look at the preimage of the point up here. And that's a family varying in a parameter of the x. So we'll talk about that.
Have you talked about fold-X yet? No.
No.
Okay.
All right? Yes?
You asked if we had foundational issues, and of
Yes.
course, cat
Anybody
is
feel
too big.
foundationally queasy here? Because the objects of this category are categories. Here's a category. So maybe this is an object in that category. Right? You can think about it. I mean, at some point you have to deal with these kinds of questions. And one of the ways of dealing with them that's at least allows us to get some work done is to say, we'll define.
So we fix some foundations, foundational system. Oh yeah, okay. Here. Okay, so we'll make this large. Okay. Maybe set theory, type theory, maybe even category theory. Just fix some foundations, right? Fix some foundations, and then if a category consists of, so C consists of the objects and the arrows, there's a notion of smallness with respect to any of these systems, right? A small category would be one where the objects and arrows form a set. or a type or an object in the category and so on. So we'll say this is small, so as a definition, if both C0 and C1 are, let's say, sets, just to be specific. And we'll say it's large otherwise. So that's just a terminology, right? But it's a useful terminology because here we would say cat is the category of all small categories. And then cat itself is not small, right? By kind of foundational principles, cat itself must be bigger. And then it will be... Yeah, sure. It's beautiful, isn't it? There's nothing wrong with that, yeah. So, I mean, you have to get around these foundational issues somehow, but that's not category theory's problem. That's the foundational issue. Yep?
C over A, or?
Yeah, C over A, or C sliced over A.
So in C sliced over A, objects are arrows into A?
Yeah.
From what? From anything else?
Arbitrary objects.
From any other object in C?
Yeah.
Okay. But not from any category?
No, that wouldn't make any sense.
Okay. And arrows in C sliced over A are?
Commutative triangles in C.
Okay.
You good?
Sliced over A means you don't use stuff from A, or?
No, it just means it's just a word. I mean, the objects of this category are arrows like this in C. So arrows, the codomain of which is A. Okay?
So the arrows in the slice are a subset of the arrows in C.
Yeah. If it's small. If it's not small, it's not a set. What the slice means? Okay. Don't be confused by the word slice. It's just we have to call it something. It says something. Okay, good. So C over A.
Objects, let's do it like this. The objects of the new category C over A are pairs consisting of an object of C together with an arrow into A. And so the A is fixed here, right? So they're pairs like that, X, F. And an arrow in C over A is an arrow, so from such a pair. I'm not going to write them as pairs, though, because it's too, what's the word I'm looking for? Well, anyway. To write them as pairs is to kind of forego the advantage of category theory, which is that we have these diagrams to work with, right? I could write them as formal pairs and so on, but really they're things like this. And then another one is a thing like this. So now what is an arrow from a thing like this to a thing like this? Well, it's an arrow in the category alpha from X to Y such that G after alpha equals F. That is, this triangle commutes. So that's the definition of the slice category. The objects are arrows. The arrows are also arrows, but they satisfy certain conditions. Good? Yes? Didn't I say that? Here. For a fixed object in C, we make a slice category over that object.
Good.
And that last statement there, that only makes sense in category C, but not in category C over A.
This.
That, yeah.
Yes. Yeah.
Right, because, okay.
That's the definition of the arrows of the slice category. Yes. Anyone interested in the slice category?
This is just a notational question. You're writing like little quote marks inside the diagram. Is that notation to say it can
Equal sign. It's an equal sign.
Oh, okay.
I just mean equal. It goes. It just means this composite is equal to that.
Okay.
Yeah, good question. Yeah.
Is there a good name for the dual of the slice category where you have arrows?
Slice. So we'll do duality.
Okay.
If the dual of anything is a code of anything.
Okay.
Unless it already starts with code, then you don't say code of
I mean, coslice is fine.
what are we doing? I think I have to do representable functors now. Oh yeah, foundational issues. Well, we'll talk about that later over a beer. No, I said the cat is, once we have a foundational scheme, then relative to that foundational scheme, we can define a notion of small and large. Then cat, we will say, is the category of small categories. Cat itself will not be small, typically, in most foundations, unless it's something perverse like Quine's new foundations, where cat can be an object in cat. Then typically cat will be large, and that's all. So that solves that evident puzzle, that apparent puzzle. Yes?
You've assigned this for homework.
Yes.
Is a large functor?
No, there's not a notion of large functor. There's a notion of functors between small or large categories, and it's a functor that takes a small category to a large category. Good. Opposite.
Here's a fascinating, but how much time do I have, by the way? Oh, great. Okay. Perfect. In category theory, there's this amazing duality. And it's really, on the face of it, the first time you see it, you think, oh, that's kind of cute, right? It's like a trivial or simple thing. But I claim it's actually a deep mathematical phenomenon, this category theoretic duality. But you can only see it through the lens of category theory. So we'll have a glimpse of a couple of instances of category theoretic duality in a couple of the later lectures. And maybe, or if you remind me at the end, I'll give you a few more pointers on duality theory. But so just to get started here, every category C has a dual category or an opposite. I'm going to use the term opposite. C op. So it's just a superscript op. And the objects in C op are the same as the objects of C. Actually, the arrows in C op are the same too. But you swap the domain and the codomain. Domain is codomain, and the codomain is a domain. This is kind of weird here, isn't it? So this is in C op, and this is in C. So the idea formally is this. If I have some diagram like this, B, C, G after F, and the identities are the same too, by the way, and this is in C, then I can regard that as a diagram in C op with the same objects, but I regard the arrows as going in the other direction. That is, I draw them the other way around because this is, although it's the same arrow, I swap now what is its domain with its codomain. So this is an arrow in C op, that's an arrow in C op, and now the composition you'll see has to be reversed because, let me give it a name, I'll write G bar to mean the same arrow regarded as an arrow in C op. And I'll write F bar to mean the same arrow regarded as an arrow in C op. But now if you look at the composition, it looks like this. It's F bar after G bar. And that is then the bar of G after F. So you have the same composition, but we've reversed the roles of domain and codomain. The one stays the same. So that's the notion of the opposite category. It's, if you like, it's really the same category, you just hold it up to the mirror or something like that, and you look at it from behind or something like that. So it's a purely formal operation on the category, but it's very useful, and like I said, it initially seems superficial, but we're going to make use of it, and you'll see what it's good for. For example, one thing it's good for is this. A functor F from the opposite of a category into another category is something like this. It takes a diagram in C to a diagram in D with the arrows all reversed, right? Because really, if this is in C, say, well, then in C up, the arrows are going the other way, and now I make a functor, and the arrows end up going that way. Okay, so that's f of f, say, and so on. So this is the notion of a contravariant functor. Contravariant functor. A contravariant functor is not a different kind of functor. It's just a functor on the dual category of the category in the domain. We don't need a separate theory of contravariant functors. It's just functors where you swap the variance here in the domain. Okay? So that's one example of the notion of a dual. And let's have some examples of contravariant functors. So let's look at the category of sets. And for any two sets in the category of sets, you can build the set of all functions from one to the other. So here we are in sets. And we have some sets here, A and B, and then B to the A is the set of all functions from A to B. And now let's observe that this is a functor. This is a functor in the argument B. That is, for fixed A, I get a functor like this, f, I use the Schrieg linear, right, f lower star from any, oops, sorry, no, that's right, from f from x to y. So given any f from x to y, there's an induced map, f lower star, from A into x, A into y. What does it do? Well, it takes some g here in this, and it maps it over to f after g. Right? G is going from A to x. F after g is going from A to x to y. That's where f lives. And this is f after g. Good? So now I claim that that's a functor. That's going to be a homework exercise, I think. This is a regular old functor. Look, the direction is going the right way. But you could also fix the other argument. So this is a contravariant functor in the argument A. So what does that mean? If I take given, so in the argument A, so what that means is if I fix B, I have, as before, f going from x to y, I'll get a map from by to bx, which I'll call f upper star. And how does f upper star work? I take some y into b, and then I have here my f, and I precompose now. Here's g, and here's f upper star of g is precomposition, g after f. So that takes a thing from y into b over to a thing from x into b. And this thing is a contravariant functor of A. It acts in this contravariant argument. Okay? So those are just claims. You can check them as homework exercises. And in fact, there's a generalization of this, which I'm going to need, and which is, anyway, good to know about because it's a very important construction. And that's the notion of a representable functor. Yep?
Yeah, it is a bit late. Let's talk about afterwards. What?
What does the bar mean?
No bar.
F bar?
No bar.
Oh, on the far left.
Why before?
Oh, it just means in the opposite
Let's talk
category.
about that later.
It's the inverse. Sorry.
No, it's not the inverse. It's a formal. It's just a formal tool. I'm not saying take a different function and come back with the inverse. I'm saying regard this function as having, regard this arrow as having other domain components. Okay.
Representable functors. This was a construction in sets, right? I take some sets, I take A and B, and I return this set. So this is a special case. A more general case is I take some category C, and I take some objects A and B in C. Okay? And now I make the set, which I'll call HOM C if I need to be specific. So this is the set of all arrows from A to B in the category of C.
Why is the set?
Because I'm assuming that C is small. If I ever say that something is a set, it means I've assumed that it's a set. Okay? So I assume that that C is small. I take this collection of all arrows like this. So you see, things are a little bit different here. This was a special case. This lands back in the category I started with. That doesn't have to happen. This lands somewhere else. Okay? But just as before, I can say fix A, and then I get a functor in B, HOM A blank, and that will take HOM A B into HOM A B. Well, let me say X here. X and Y. X and Y for any X goes to Y, just by composition, just as before, by composition. Right? If I have a map from X to Y in C, and I take an element in this set, well, that's just some thing here coming out of A, and I compose, and I get something like this in this set. So that's my functor. It's called the representable functor of A. Representable functor of